Hello, and welcome back to the course Physics 123 Quantum Mechanics 1. So before we proceed with today's lesson, let us review some of the key concepts that we have discussed in the previous lessons. So these concepts are needed for this current lesson. So we have discussed about the Schrödinger equation, which is just the quantum mechanical analog of Newton's second law of motion. So it is an equation of state. And in quantum mechanics, we represent the state by a wave function. So statistically, we can also interpret the wave function as the probability. So in this specific equation here, this will give you the probability of finding the position of the particle x between A and B. We also have discussed about the Copenhagen interpretation, which is the correct interpretation of quantum measurement. So before you measure something in quantum mechanics, the value of your variable is not actually fixed. So if you are measuring position, before the measurement, the particle is not really anywhere. The particle's position is indeterminate, and the act of measurement itself forces the particle to take a stand, and therefore the act of measurement produces the measurement. So today's lesson is on the probability of random variables. Since we have discussed in the previous lesson that quantum mechanics is all about probabilities, we need to review some of the key concepts in probability. So we will encounter random variables, two types of random variables in this course. We have discrete random variables and continuous random variables. The position x and momentum p and any other physical quantities derived from them are continuous variables, while energy, angular momentum, or spin angular momentum are discrete variables. So let's first start with discrete variables. So if you have a discrete variable j representing an event, the probability of an event j to occur is given by this equation. So n sub j here is just a number of occurrences of event j, and n is the total number of occurrences of all events. Of course, if you add the probabilities of all of the events, you should get 1 or 100%. So there's a 100% chance that an event will occur. The event with the maximum probability is what we call the most probable event. So if you are to bet on which event is likely to occur, the safest bet is the most probable event, since it has the highest chance or probability of occurring. The mean or average value of an event j, or in quantum mechanics we call that the expectation value, because this is the value that you expect. Usually you expect the average value, the average event. So in this case, the average value is just the event multiplied by its probability and sum over all the events j. So this is actually just similar to the regular average or mean, where you add all the variables, divide by the total number of variables. But in that formula, you assume that they have the same probability, say 1 over n. But in this case, we take into account the probability of each of the events. So essentially, this formula is like a weighted mean. So you get the weight of each of the event. In general, if you have a function of j, the expectation value or the mean or average value of that function is given by this equation. So you just replace j here by your function f of j multiplied by its corresponding probability. So we'll encounter this equation more often in the next chapter. One property of discrete variables is standard deviation. So essentially, it's the deviation or spread of a distribution from the mean or average value. It is defined as this expression. So this is expectation value of the square of the event, j squared, minus the expectation value of j raised to the power of 2. So in physics, we call this uncertainty. So the larger the spread or the larger the deviation from the mean, the greater the uncertainty, the less accurate are your data or your results. So this formula is true for all variables, discrete and continuous variables. So if you have a large uncertainty, so if this is your distribution, then it has a large uncertainty. So most of your values are widely distributed over a wide range. So some of the values are very far from the mean value. Some are very close, but there are also values that are very far. So if, for instance, this is a measurement, data, then it would entail that your repeated measurements are not accurate because it has a large deviation from the mean. If you have a small standard deviation, on the other hand, then your distributions will somewhat look like this. If you'll notice, the standard deviation or the spread is just very small, meaning most of your values are close to the average or mean value, and therefore it will entail accuracy. So let's have an example for discrete variables. So rolling of a dice. So suppose you roll a single die and you roll it 10 times and you record the outcome. So there are only 6 possible outcomes in rolling a die: 1, 2, 3, 4, 5, and 6. So if you're asked to find the probability of getting a 3, then based on our formula, it's just the number of occurrences, occurrences of getting 3 over the total number of occurrences, which is just the 10 rolls or 10 events. So this will give you a probability of 30%. So the 3 in our data occurs 1, 2, 3 times. So you'll have a probability of 3 over 10 or 30%. You can actually get the probability for each of the possible outcome. For 1, 40%, since it occurs 4 times. 1, 2, 3, 4. And then for 5, it's 0% because it doesn't occur in our specific data. And if you add all of those data, you must get 100%. So in this scenario here, our most probable outcome is 1 because it has the highest probability, which is 40%. But you must take note that this is only for a specific sample of 10 rolls. If you do another 10 rolls, then your outcomes could change and your probabilities could actually change. But if your number of rolls become very, very large, then actually all of these outcomes become equally probable. So each of them will have a probability of 1 over 6. So let's now go to continuous variables. So if you have a continuous variable x, the probability that your variable x lies between x and x plus dx is given by this expression. So rho of x dx. And if you put a limit to this one, you integrate it over a certain limit, say a to b. So by the way, rho here is what we call our probability density, probability per unit measure. In this case, our measure is x, say position. But probability density can also be probability per unit momentum, probability per unit energy. So depending on your differential measure here. So in our previous lesson, we have related the probability density to the absolute value of your wave function squared, absolute value of psi squared, and we will relate that in the next lesson. So if you integrate this over from a to b, then you will get the probability that the value of x lies between a and b. So if x here is your position, then This essentially gives you the probability of finding the position between A and B. So of course, similar to the discrete case, if you add all of the probabilities, so you integrate over all space, all possible values of x, say from negative infinity to positive infinity, then you should get 1. So there's a 100% chance that you will get a value of x. So sometimes we call this the normalization condition, since in mathematical physics we usually uh, pertain normal to either perpendicular or 1. So since the value of the integral is equal to 1, so essentially it normalizes your probability density to 1. Similar with the discrete na case, if you want to get the average or the mean or the expectation value of your continuous variable x, then you multiply it with the probability and you, instead of summing, you integrate over all possible values of x. And again, if you have a function of your continuous variable x, the mean or expectation value of that function is just similar. You replace x by your function f of x in the integral. So similar with the discrete na counterpart, we will encounter this equation more often. Okay, so let's have an example. So consider the probability density distribution given by this expression, where A and lambda are positive real constants. So the only variable here is x. So you are asked to find A, the value of A, the expectation value of x, the expectation value of x squared, and the standard deviation sigma, and you are asked to sketch the probability density distribution function, rho of x, and find the probability that x is within one standard deviation. So for this example, we can use this useful formula. So if you encounter an integral of this form, where v is an integer, then the answer, the evaluation of this integral is just gamma of v over beta, which is just a constant to the power of v. The gamma function is just related to the factorial function. So gamma of v is actually v minus 1 factorial. So if you have gamma of 3, then that is 3 minus 1 or 2 factorial. And gamma of v plus 1 is v gamma of v. Okay. So for letter A, you are asked to find the constant A. And in we actually call that constant A as the normalization constant. So in order to solve that, we use the normalization condition, rho of x dx. So given our probability density function, rho of x, so we use this formula. So substitute this term here inside our integral. So this is our integrand actually. A is just a constant, so we can take it out of the integral. And then we have inside the integral e to the negative 2 lambda absolute value of x dx. And this is equal to 1. Okay. So how do we evaluate this integral? So before evaluating an integral, there's a neat trick that you should check first before, so that your life will be easier. So you should check if your integrand is either even or an odd function. So not all functions can be even or odd, but there are functions that can be even or odd. In this case, this is actually an even function. And our limits are also even, from negative infinity to positive infinity, or from negative a to a. So that's the definition of an even limit. So if you have an even function, even integrands, sorry, and even limits. So by the way, our definition for an even function is like this. If your function, if you replace your, say, function, the variable of your function, by negative, and it's just equal to the original function, say f of x, then that's the definition of an even function. The odd function, on the other hand, becomes negative if you replace the variable by, say, negative x. It becomes negative f of x. So for instance, x is odd, because if I replace x by negative x, obviously it becomes negative x. X squared is an even function, because if you replace x by negative x, you square it, it just becomes x squared. So x cubed is odd, x to the fourth is even, and so on. Sine theta, the sine function is odd, the cosine function is even. So if you have an even function, even f of x, and you integrate it over an even limits, then even functions are actually symmetric, while odd functions are anti-symmetric. So for instance, this is an example of a symmetric function. That one. This is an example of an anti-symmetric function. So symmetric, anti-symmetric. So take note that the integral of a function is just the area under the curve, this area here. So if you have an even function, you can just integrate half of the function and then multiply by 2, because the area under the curve here is just equal to the area under the curve here, so times 2 lang. So if you have an even function and you integrate it over an even limit, then you can just integrate from the half of the limit, say from 0 to infinity, and multiply by 2, because they are symmetric. The integral are symmetric. On the other hand, for this is even, this is odd. For odd functions, you will notice that they are anti-symmetric. So the area here is positive, the area here is actually will give you, the area under the curve will give you a negative value. So therefore, positive area, or negative integral, then you will get 0. So if you integrate an odd function, or if you have an odd integrand integrated over an even limit, then your result should be 0. So no need to integrate. So just check. So every time you encounter an integral, you should check the integrand first and the limits. If you have even limits, so check if the integrand is even or odd, because you don't need, if it's odd, if the integrand is odd and your limits are even, then you don't need to integrate, because that will give you 0. Okay, so going back to our equation here, even integrand, even limits, so therefore I can just multiply by 2 and integrate from 0 to positive infinity. So you will notice here that I no longer put the absolute value sign, because I'm just integrating from 0 to positive infinity, where the values of x there is positive. So no need to put the absolute value sign. Okay, so let's change variable. So this is just a simple exponential function. So we let u is equal to negative 2 lambda x. Therefore, x is equal to negative u over 2 lambda, and dx is negative du over 2 lambda. So when we change variable, so this is now e to the u, and dx is negative du over 2 over lambda, and we take negative 1 over 2 lambda outside of the integral. There's a 2 here, and that will give you negative a over lambda e to the u du is equal to 1. So our limits now, if x is equal to 0, u is also equal to 0. If x is equal to positive infinity, u becomes negative infinity. This is negative infinity. So this integral, the integral of e to the u du, is just e to the u evaluated from 0 to negative infinity, and this is just e to the negative infinity is 1 over e to the infinity, or 1 over a very large number, which is 0. Then e to the 0 is 1. So essentially, this integral is negative 1. So negative 1 multiplied by negative 1. So this becomes a over lambda is equal to 1, and therefore a is equal to lambda. That is our normalization constant. Okay. So for letter B, we are asked to find the expectation value of x, expectation value of x squared, and the standard deviation. So to find the expectation value of x, so we use this formula here. So the mean value is this one, this equation. Okay. So substitute the value of rho here, where our a now is equal to lambda. So a now is equal to lambda. So you take out lambda out of the integral, and then you will have from negative infinity to positive infinity of, you have x, and then you have e to the negative 2 lambda, the absolute value of x dx. Okay. Again, let's check. We have an even limit. Let's check our integrand. Okay, x is an odd function. E to the negative 2 lambda absolute value of x is an even function, because if you change, replace x by negative x, due to the absolute value sign, it's still x, positive value. So what happens when you multiply an odd function and an even function? You get an odd function. So it's an odd na integrand, or an odd na function. If you multiply two odd functions, it becomes an even function. If you multiply two even functions, it becomes an even function. So therefore, odd integrand, even limit, so this is 0. No need to integrate. So this means that our average value of x is 0. So this could only mean one thing. If your average value or mean value or expectation value is 0, then some of the values will be above 0, positive. Some of the values will be negative, below 0. So that the mean value, the middle value, something like that, is 0. Okay. How about the expectation value of x squared? So for the expectation value of x squared, the formula is similar, but instead of x, you have x squared. Okay, sorry. So essentially, for x squared, it's just squared there. So in this case, x squared is an even function. E to the negative 2 lambda absolute value of x is an even. So even times even, you get an even function. So therefore, even integrand, even limits, I can just multiply by 2 and integrate from 0 to positive infinity. So you have x squared e to the negative 2 lambda x. I no longer need to use the absolute value sign, because we are in the range 0 to positive infinity, where all the values of x are positive, dx. Okay, so in order to evaluate this integral, we need to go back to our the useful integral that I have shown you earlier. Okay, this integral. So in this case here, this is x squared, and this is x to the v minus 1. Therefore, our v is 3. Our beta here is 2 lambda. So beta is 2 lambda. Therefore, the evaluation of this integral is just gamma of 3 over beta, which is 2 lambda to the power of 3. Gamma of 3 is just 3 minus 1 factorial, or 2 factorial. So 2 over, okay, there's a 2 cube here, there's a 2 here, so therefore there's a 2 squared na lang, and you have lambda cube. Okay, so this is our integral, the result of our integral. When we multiply that by 2 lambda, so you will get 1 over 2 lambda, lambda cube, lambda squared. So this is the expectation value of x squared, 1 over 2 lambda squared. Okay, so that one, 1 over 2 lambda squared. So how do you get now the standard deviation? So standard deviation is just given by this formula. So the difference of the expectation value of x squared minus the expectation value of x squared, and you take the square root of that difference. So since 0 ang ato ang expectation value of x, so this term here is 0. So therefore, the standard deviation is just the square root of this one, the expectation value of x squared. So the square root of that is 1 over square root of 2 lambda. Okay. For the next problem, we are asked to sketch our probability density function. So you will notice this is an exponential decay, e to the negative x. That's an exponential decay. So from 0 to positive infinity, it's an exponential decay. And since this is an even function, it should be symmetric. So it will look like it will also decay towards the negative infinity. So this is an even function, so this should be symmetric. So you will notice at x is equal to 0, e to the 0 is 1, so the maximum value of our probability density is a or lambda here at x is equal to 0. It just so happened that x is equal to 0 is also our average value or expectation value. So the spread from the mean, which is 0, is sigma. So sigma here and also a sigma here. So this is negative sigma position, positive sigma position. So this is one standard deviation. This is one standard deviation to the right, and this is one standard deviation to the left. Okay. For the last problem, you are asked to find the probability that your value of x lies within one standard deviation. So what the problem actually means is find the probability that x is between negative sigma and positive sigma. So you find the probability that x is within one standard deviation to the left and one standard deviation to the right. So the area that this integral here, the integral of rho of x dx from negative sigma to positive sigma, is actually this area here, the area from negative sigma to positive sigma. So this area here, that's actually the probability that we are trying to look for. Okay, sorry, I already broadcasted the answer. So the probability is just this one. Okay, so it's from negative infinity to positive infinity. So our rho of x is just this one, where a is equal to lambda. So we take lambda out of the integral from negative sigma to positive sigma, then e to the negative 2 lambda absolute value of x dx. Again, even integrand, even limits. Therefore, I can just integrate in 1/2 of the interval, so from 0 to sigma, and multiply by 2. So e to the negative 2 lambda x dx. So I no longer need to use the absolute value sign because I'm only using positive values of x. Okay. So similar with what we have, we change variables, and if you change variables, your dx is just negative du over 2 lambda. So you take it out of the integral, the negative 1 over 2 lambda factor for dx. So you have 2 lambda, so negative 1 lang outside the integral. And you have 0 to sigma of e to the u du. Okay. So basically, this is just an exponential term, e to the u evaluated from 0 to sigma. So our sigma here is this one, 1 over square root of 2 lambda. Okay, sorry, I forgot to change our limits. We should change our limits because when we change variable here, u is equal to negative 2 lambda x. So when x is equal to 0, u is equal to 0. But when x is equal to sigma, where sigma is this one, when x is equal to sigma, which is 1 over square root of 2 lambda, u becomes, so if this is 1 over square root of 2 lambda, then this becomes negative 2 over square root of 2. So this should be our upper limit, not sigma. Negative 2 over square root of 2. Okay. So evaluating this gives us e to the negative 2 over square root of 2 minus e to the 0, which is just 1. And since there's a negative sign here, then therefore the probability is just the negative of this one, which is just this one, 1 minus e to the negative 2 over square root of 2, which is approximately 75.7%. So that is actually the area of this shaded region here. So there's a 75.7% chance that your value of x is within this region. So if you are asked to find the probability that x lies outside this region, then you just subtract 75.7% from 100%, and you will get a value of 24.3%. So that's the chance that x lies beyond sigma and beyond negative sigma. Okay. So that ends our lesson for this session. So for our next lesson, we will be discussing about the normalization of the wave function. So we have now encountered how to normalize a probability density. So we will now relate that to our wave function. So that's it for today. Thank you for listening, and I will see you in our next session.